While we are all joining this event from our own location, I would like to acknowledge that we are meeting on the lands of the Wurundjeri people and the Bunurong people of the Southeast Kulin Nation. I would like to pay my respects to the elders past, present and emerging, and to all First Nations communities joining us today. Well, hello everybody. Welcome to our second episode of A Night at the Observatory. Thank you all so much for joining us tonight. Just a quick introduction before we get things started tonight. My name is Jamie. I'm the Outreach Coordinator at Mount Burnett Observatory. With me tonight I have Neil. Give us a wave, Neil. Neil is our Director of Astrophotography at MBO. On my right, while we are all joining this event from our own location, I would like to acknowledge that we are meeting on the lands of the Wurundjeri people and the Bunurong people of the Southeast Kulin Nation. I would like to pay my respects to the elders past, present and emerging, and to all First Nations communities joining us today. Apologies, everyone. Just had a minor glitch. So back to introductions. So we've introduced Neil. On my right, I have Andrew. Say hello, Andrew. We've got Liam down in the bottom left-hand side there as well. Liam is one of our youngest members of our outreach team. He's also one of our young observers. We've got Drew in the middle on the bottom row there. Say hello, Drew. And we've got Steve with us as well. Give us a wave, Steve. Thank you very much. Well, as I said, thank you very much to everybody for coming along tonight. We hope you're going to have an amazing experience with us. And we're going to get started. So just going to give you a bit of an overview of MBO. So we are sponsored by the Cardinia Shire Council. So we thank you guys very much for your support. So a little bit about us. MBO is run entirely by volunteers. So everybody that you can see here tonight is a volunteer at MBO. Director of Astrophotography at MBO. So the grounds of MBO is based in the Dandenong Ranges near Cockatoo, and we've got around 550 members. That makes us the second largest astronomical society in the state, after only the Astronomical Society of Victoria. We don't want to compete with those guys. Our focus is on community engagement, our outreach events just like this one, and giving our members different ways to share and explore their passions and interests in astronomy. Diversity is a key part of our identity as well. 40% of our membership base identifies as female, which is really, really good. And we've got quite a few young members as well. As I mentioned, Liam is one of our young observers. So just a little bit about MBO. The observatory was built by Monash University in the early 1970s. It was for the purposes of providing the students of Monash University with the ability to conduct research. So their research was primarily on variable stars. So we've got quite a few other things on the grounds of MBO as well. So we've got a few domes. We've got a larger one and a smaller one as well. So in the larger dome, which we call the Monash Dome, after the Monash University that built it, that one housed a 16-inch wooden barrel telescope. So when I say 16-inch, that just means that the size of the mirror was 16 inches. We've got one in there now that is an 18-inch metal barrel telescope. So the mirror in the back of that one is 18 inches or about 45 centimetres across. We've upgraded the grounds, or the grounds were upgraded later on as well after the dome was constructed. So there's now a log cabin on the grounds, which was used primarily to provide students with a place to shower and sleep while they were conducting their research. You can see on the bottom right-hand corner there as well, we've got what we call the chook shed. So that one controlled a smaller computer-controlled telescope. So that one was a bit easier for the students to use than the one that's in the Monash Dome now. So you can see the pictures on the bottom there as well. The one in the middle is the original telescope that was in the Monash Dome, and the one on the left-hand side is the one that lives in there today. So in 2011, our 5 founding members, who were originally part of the Astronomical Society of Victoria, or the ASV, negotiated with the owners of the land on which MBO is housed. So as I said, in the Dandenong Ranges in Cockatoo. They took over the lease and started what would become one of the most active astronomy clubs in Victoria. So as I mentioned, we're now the second largest astronomical society in Victoria. So our mission is to preserve Mount Burnett Observatory for the benefit of the Society's members and the community, to educate the public in the science of astronomy, disseminate astronomical knowledge and encourage the observation of the universe, to provide facilities to support members of the Society in the practice and study of astronomy, including astronomical research, to collaborate actively with other institutions and groups to the benefit of the Society's activities, to bring into closer association persons and institutions engaged in astronomy in order to cooperatively advance our knowledge, and to pursue any other arrangements and activities conducive to the above purposes. So basically, we just want everybody to learn as much as they can about astronomy, and we want to share that knowledge with as many people as we can. So we run quite a few activities as well. We run about 80 events a year. That includes members' nights. We have meetings as well, including outreach events just like this one. We have a few off-site activities as well. So we've run events at Science Works in the past. Some of you may have been to the Astrolight Festival. We were involved in that. We have several special interest groups, so that includes, as I mentioned before, outreach. We have a deep sky program, so looking at the fainter objects of the universe. We run astrophotography. Neil, as the director of astrophotography, is in charge of that one. We have an astro arts group, radio astronomy, so that lets us listen to the different sounds that the universe has to offer. And young observers. Liam is, as I said earlier, part of our young observers program, and that one aims to provide astronomical knowledge to the younger members of our group. We also have annual open days to show the local community who we are and what we do. Obviously, we can't run viewings on those open days, but we can show everybody the grounds and what we have to offer. We've got several social media platforms. So we have Instagram and Facebook and YouTube. As some of you may know, some of you may be watching us on YouTube. And we have a new online streaming at the moment, as you'd all know, so that enables us to reach more people during the current climate. So our goals for the future. So we want to keep growing our membership and reach out to those who love astronomy. We want to continue to engage with the community and public in general to provide education and entertainment. We want to build on the strength of our diversity and continue to make MBO more accessible to as many people as we can. We want to improve and add to the facilities that are there to provide members to help pursue their interests. And we want to provide a stable, long-term future for the Society and members. So you guys can help out with this as well in a few different ways. So you can become a member. You can volunteer your time as a member with whatever skills you have. It doesn't have to be astronomy related. We run a few working bees on the grounds as well. So if you've got any experience that could be useful for that, you're more than welcome to come up and help as a member. You can make donations or purchase our merch. You'll notice in the top right-hand corner there, we've got a t-shirt. So that's an example of some of the merchandise that you can get from our store, which is at mbo.org.au. You can follow us on social media and share our posts with your friends, spread the word, spread the love, and you can tell your local government how important we are to you as well and request that they support us as well, which is really, really important for getting financial support should we need it to improve the grounds. So that pretty much sums it up for who we are and what we do. So I'm going to hand over now to Neil. As I said before, Neil is our Director of Astrophotography at Mount Burnett Observatory, and he's also an active member of the outreach team. He's been a professional photographer for the last 15 years with experience in digital photography. He's had a love of space and astronomy, since childhood. His father introduced him to Carl Sagan's Cosmos, and he loves to share his passion for the universe with others who share the passion. He enjoys teaching others the art and science of astrophotography. And Neil is actually a 3-time category winner of the David Malin National Astrophotography Awards, and he's been published numerous times in Discovery magazine in the USA and Australian Geographic magazine. So Neil is extremely qualified in his field, and he's going to show you a little bit more about that later on tonight. So Neil, over to you.
Thank you very much, Jamie. I'm just going to start we've got a bit of audio feedback again.
Which is at mbo.org.
So if any of you folks have got the stream open, just mute it, please. Thank you. Right, so yes, going to play another series of mini documentaries. Those who would join us the first time would remember those. This time we're starting off with a guide to where MBO is in the universe. Sorry, folks, I was just informed that yet again I didn't share with audio. So I'm terribly sorry about that. It's all new to us, all this sharing with streaming. So I shall just start that one up again so you don't miss out on the audio this time. Welcome to Mount Burnett Observatory, our little observatory in the hills. But where is it really in the universe? Let's take a journey and find out. The Earth, our home in the universe. It's 12,700 kilometers across. That might sound like a big number, but it's nothing on the scale of the universe. Let's travel to the Sun, the center of our solar system and the source of all life on Earth. It's 1.4 million kilometers across, or 109 Earths wide. Now we travel out through the solar system, all the way past the orbit of Neptune, 4.5 billion kilometers, or 4 light hours. We're just getting started on our journey though. Let's pull back now to the local area of the galaxy, with the nearest stars only about 10 light years away. But we're hampered by the sensitivity of our eyes. Let's turn up the brightness so that we can see all the stars you would see through a pair of binoculars from dark skies. Every star you see here is real and has been catalogued by astronomers. This region is approximately 1,400 light years across. As we pan around, you can see the depth and structure of the stars in the Milky Way, and how the stars come together in a flattened area along the plane of the Milky Way galaxy. Now let's show all the stars we think exist but have yet to observe, and pull back until we can see the whole of our Milky Way galaxy. Our galaxy, our island in the cosmic ocean, has approximately 1 to 400 billion stars and is over 100,000 light years across. Travelling further now, we cover the vast distances between the galaxies. This is the local cluster of approximately 30 galaxies, most of them dwarf galaxies, but including our large neighbour, the Andromeda Galaxy, as well as the Triangulum Galaxy and the large and small Magellanic Clouds. The Andromeda Galaxy is approximately 2.5 million light years away. Now, speeding up, we continue our journey out through the universe. Every dot you see here is a galaxy, and every galaxy contains hundreds of billions of stars. The scale of the universe is truly vast and beyond the comprehension of a human brain. We travel past hundreds of billions of galaxies, all the way to the edge of the visible universe, 13.4 billion light years away. Now, let's return home. Welcome home to our Earth, the only speck of dust in the universe we know to have life. It's precious and we must protect it.
Well, thank you very much for that, Neil, and such an important message at the end there as well. We only have one Earth and we need to look after it because we don't have another one. Moving on now, we have a pre-recorded talk from Drew. Some of you may have seen his segment in our last Night at the Observatory session. So the series is called Astronomy Basics, and episode 2 is about the Earth and the Sun. So Drew has been an active member of the outreach team for some time now, and he's been involved with events as diverse as the Astrolight Festival at ScienceWorks, as I mentioned before, and the Belgrave Lantern Parade. Some of you local to the Belgrave area would know all about that one. Drew loves showing members of the public what can be seen from Earth, the science behind astronomy, as well as talking about the stories connected with the stars. He's great at encouraging beginners, having been one himself, as we all have been. Like many of our members, he lives in the Dandenong Ranges, where the skies are great for viewing when there's no clouds. And apart from astronomy, Drew loves movies, Dungeons and Dragons, and his cats. So some of the cats on our team might be making a bit of an appearance tonight. So keep an eye out for those. But for now, I'm going to hand over to Drew. All yours.
Welcome to the second in a series of short presentations. In the first presentation, I showed you the Earth and how it rotates on its axis. This makes everything in the sky, including our Sun, appear to move in the other direction relatively. This is all quite correct. However, it's not quite the whole story, so let's look a little bit closer. The Sun is a star, like the other stars in the sky. However, it's more than 250,000 times closer than the next nearest star. The Sun appears to move around the Earth, but actually the Earth orbits around the Sun. This was discovered by a man named Nicolaus Copernicus, although he wasn't the first to come up with the idea. But he was ridiculed for it in his day. After all, everybody knows the Earth is the center of everything. And besides, his circular orbits didn't quite align with the problematic observations made by other astronomers. It wasn't until some 70 years later that a man named Johannes Kepler discovered that the Earth and the other planets move in elliptical paths around the Sun. All of a sudden, observations started to make sense, and Copernicus' ideas started to be accepted. The amount of time it takes to move around the Sun once is called a year, and that takes 365 days, 5 hours, 48 minutes, and 45 seconds, approximately speaking. This is a bit hard to remember and work with, so we use a 365-day year to round it off. To cater for this rounding, we have a special concept where every 4 years, in February, we add an extra day. These special years are called leap years. This brings us much closer to the actual time it takes, although it overcompensates slightly. So as a result, in century years ending in 00, only the fourth one of those is a leap year. This makes things pretty close to what actually happens. Astronomers also have a concept called leap seconds to fine-tune things, but let's not worry about complicating things that way. Now here we have the Earth spinning perpendicular to the Sun. This is not quite right, so let's take a bit of an adjustment. The Earth is actually tilted at an angle of 23.5 degrees relative to the Sun, and this is important, as we'll see shortly. In the previous presentation, I mentioned the equator, which is an imaginary line around the middle of the Earth, separating the northern and southern hemispheres. There are two other important lines to consider here. These are called the tropics, or turning points. In the northern hemisphere, at 23.5 degrees north, we have the Tropic of Cancer. And then, in the southern hemisphere, at 23.5 degrees south, we have the Tropic of Capricorn. The Sun appears to move between these two lines as we go around it. In June every year, on June 21st, we have what's called the June solstice. At this point, the Sun is shining directly on the Tropic of Cancer, giving the northern hemisphere its summer solstice, or longest day of the year, and the winter solstice in the southern hemisphere. On the other hand, on December 21st, the opposite time of year, the Sun is shining directly on the Tropic of Capricorn, giving the southern hemisphere its summer solstice, or longest day of the year, and the northern hemisphere its winter solstice. On the other hand, halfway in between these 2 points, we have the equinoxes, or equal days. At these points, the Sun is shining directly on the equator, halfway between the two tropics. This happens on March 21st and September 21st. And between the solstices and equinoxes and the axis and everything here, we have our seasons helping us to live. Now this ends this presentation, so I'll join you again in the Q&A. Thank you.
Well, thank you very much for that, Drew. Going to hand back over to Neil now. I believe you have some information for us about the type of light that astronomers use.
Yes, indeed. We're going to be answering the question, which some of you may never have even asked, is why do astronomers use red light? Why do astronomers use red light? This is something you might have seen before if you've ever been to a star party, or you might have seen it in the movies where maybe the submarine on the bridge has got red lights everywhere. Why do they do that? Why do astronomers use red lights instead of white? Well, it's all to do with a biological function called dark adaptation. Our eyes are amazing pieces of equipment that can see detail in all kinds of brightness levels, from a dingy theatre to a brightly lit summer's day at the beach. How does our eye adapt to such a significant difference in brightness and still see? Well, there's two most important features. One being the pupil dilation, which is something that you're familiar with. When a light shines in your eyes, your pupils immediately contract, much smaller, so that stops a lot of the light from getting through. This happens quite quickly, as you can see here. The other technique is something called bleaching. The retina at the back of our eye is lined with lots of photosensitive cells, cells that react to light. Now, how can you tune those so that they react less to bright light and more to faint? Well, along with these cells, there are chemicals in the eye, and they do what's called bleaching. Much like grains of silver on film, They turn dark when exposed to light, and that prevents some of the light from getting through to the cells. It blocks some of that light. You can see an example of that here with this white triangle on a black background. If you stare at the triangle for a few seconds, the cells get bleached in that area. But if we turn off the white triangle, then a persistence of that white triangle stays. It's a part where the eye is bleached, and that fades over time. Well, to get dark adapted, we need that to fade away completely, and that can take up to half an hour. That's part of the dark adaptation process. But we still want to see what we're doing. We still want to see our camera, we still want to read our star charts. How do we do that without using any light and therefore bleaching the cells? Well, the bleaching chemicals in our retina don't react as strongly to dim red light. So we can use that dim red light, like this headlamp here, in order to see in the dark without losing our dark adaptation. That's why it's important not to look at your phone screen while you're stargazing. Using a red torchlight to read your star charts or to look at the buttons on your camera will preserve that night vision. So where do you find a red light? Well, I bought this little headlamp from my local supermarket for about 30 bucks. It's very handy, I can use it hands-free. But if you want something that's a little bit cheaper and in more of a torch form, then you can get these from our shop at mbo.org.au/shop. So grab yourself one and be prepared for your next night of stargazing with the best possible sensitivity to your eye.
Well, thank you very much for that, Neil. I think red torches are very cool, and that just confirms it. All right, going to hand over now to Liam and Andrew. As I said before, Liam is one of our young observers. He's been an active member at Mount Burnett Observatory for the last couple of years. He's a regular participant in Young Observers, as well as being part of the outreach team and the new MBO Coding Club. He's enjoyed carrying a lantern at the Belgrave Lantern Parade the last couple of years. He likes showing members the joys of the sky through a telescope and dabbles in a little bit of astrophotography when the conditions and time allow. His favourite planet is Mars, and he has a special interest in the rover Curiosity, which we'll hear a little bit more about later on. And he's eager to see how Perseverance performs when it lands on Mars, which again you'll hear a little bit more about later on. As for Andrew, he joined MBO back in 2015 and has been actively involved in outreach for the last 4 years. He was a secondary school teacher for 40 years and taught astronomy as part of the science course at most levels. He had the advantage of doing this during the years when space exploration really took off, no pun intended. And every year, Andrew needed to change his notes and content as another space probe arrived for the first time at each of the planets in the solar system, which was a great way for him to learn. He's also run viewing nights for his students and the public during his spare time on the grounds of the school he taught at. He also ran an overnight camp at Summers to observe Halley's Comet, which some of you might know a little bit about. In his spare time, Andrew has been a basketball referee for 40 years. So that's about it for background for Liam and Andrew. Over to you now, guys.
Okay, thank you very much, Jamie, and welcome everyone. The next part of the program is live and right up to the moment, so anything could happen. Liam and I are going to take you to Mars and see if we can teach you a few things about that. So bear with me, and I'll just turn on share screen. And there we go. Okay. It should have happened then. There we go. Now, hopefully you can see Redshift. Just a moment. I'll just check. Yep. Okay. And we'll go to full screen. Okay, this is actually what you would see if you were out in the open and the sky was clear and there was no extra lights around. You would see that Mars is just rising right now. This is the current time. Oh, hang on. Yes, that's right. So Mars is just on the horizon. By the time we finish the show or the presentation, you will be able to go outside. I believe there are enough gaps in the sky tonight, certainly in my area, and you should be able to see Mars out towards the east. So easy to see because it's got that red or orange tinge to it, and at the moment, because it's so close to us, it's the brightest object in the sky besides the moon, and I don't think the moon's up yet. So a very good night for seeing Mars. If you happen to have a telescope or binoculars, you may be able to see some of the features on the planet if you're patient enough. All right, let's have a closer look at Mars. I'll just center it. There we are, and we'll zoom in and have a look at what you would see if conditions are ideal. There we are. There's the planet. As you can see, lots of craters. There's not much there to protect the planet. Jupiter would offer some protection. Its moons are too small, however. And the other thing, because it doesn't really rain or anything like that on Mars, the craters that are even very, very old are still quite easy to see because there's not that much erosion. About the only thing that does happen is dust storms, and they may hide some of the planet's features to us for a while, but they don't change much. Just down the bottom here, you can see the very tip of Valles Marineris, which I'll show you a better picture of later. We're actually looking at the planet side on. There's the South Pole there. And because it's summer on Mars at the moment, that means that the sun is lighting up the southern regions. The North Pole, which is around this side, is in total darkness at this time of the year. A Martian day is about the same as ours, about 25 hours. So even while we're watching, we may see a slight change in the features, or we will later. Mars' gravity is considerably less than ours because the planet is barely or just over half the diameter of the Earth, 6,800 kilometres. And as a result, even though it's made of similar materials to the Earth, if you went there, you'd weigh just over a third of what you do here. So a great way to lose weight instantaneously, although it may take you 18 months to get there. As the crow flies, at the moment, Mars is just over 62 million kilometres away, or 3.5 minutes away if you were travelling at the speed of light. So it's at one of its closest points. In fact, it's what we call in opposition. In fact, it'll be on the 14th, just this week. It will be right in line. I'll quickly show you what we mean by that. Let's travel to have a look at our solar system. Here we go. There's Mercury, Venus. Right, we're drawing back to have a look at the solar system. We'll just let this run for a little while. There we go. And you can see what it's like. I'll just stop it. Hang on. There we go. Stop it there. No, it doesn't let me. I've played with this before. And there we go. Let's try what happens now. Let's take it to now. Okay, and there we have our solar system with the orbits of the planets and some of the smaller stars shown. I'll stop that. Dear. This is the problem with doing things live. It always works when you practice it. Okay, let's take it to current again. There we are. Now, hopefully it won't do anything silly. Zoom in. At the moment, we can see the position of the Earth here and Mars. But you remember last month we looked at Jupiter and Saturn. You can see that they're nearly in a line. And when the Earth moves around a bit further, later this year, they look to be almost in the same region of space. But let's zoom in a little closer. There we are. Now we can see the orbits of the Earth and Mars. And you can see that as we speak, here's the time now. There's the Sun, there's the Earth, there's Mars. We're almost exactly in a line. If I quickly change this to the 14th, Sun, Earth, Mars. Almost, it is, in fact, an exact straight line here. Okay, now I'm just going to quickly center the Earth and zoom in a little bit. And I believe we can now turn around. Let's turn the solar system on its side, and there we can see it even better. All right, here's Mars, here's the Earth, there's the Sun, almost in fact, they are in an exact straight line. There you go. And that's what we call at opposition. All right, let's go back to another view again. If we have a look at that, the Earth takes a year to go around. Of course, Mars takes about 2 years. So in another couple of years, it'll be in, or around about 2 years, it'll be in opposition again, but it'll be further around its orbit. And you can see once we get around here, the distance increases. 2 years ago, we were back around here when it was in opposition, and it was about the closest it's been in a long time. And it really, really was bright, and it seemed larger in the sky. In a couple of years or thereabouts, when it's in opposition again, it won't be quite as spectacular. In fact, it won't be this close for at least another 15 years. So make the most of it. Now let's fly to Mars and have a closer look. Here we go. And while this is happening, I should mention that we appreciate the permission of the Redshift people. Redshift is the application we're using to show you all this. It's a really good one, as you can see, very good graphics. Once you have a bit of a play with it, it's easy to use. It's really good. Now there we can see Mars, not quite the same angle as we were looking at before. That's more like that. Where's the pole? Yeah, we're looking at more like that. There's the South Pole, and you can see the North Pole is in darkness, but it's much larger. And that is, of course, because it's been cold there for a long time. It hasn't had sun on it for a long, long time. And the ice cap is actually becoming wider, not only with water ice, and about 70% of it is water ice, but then the other percent is mainly dry ice or solid carbon dioxide. So during the winter, that builds up and builds up and builds up, and the ice cap can become very, very wide. As summer approaches, though, as it has in the southern hemisphere, you can see now the South Polar cap is quite small. All that carbon dioxide didn't melt, it sublimed. So it went straight to a gas, and that spread back through the atmosphere. The atmosphere is about 90% or more, 99% carbon dioxide, but it's very thin, very thin. If you are on the surface of Mars, the atmospheric pressure is about a 160th of the Earth, or in scientific terms, it's 0.006 atmospheres, very, very, almost vacuum-like. So you wouldn't be able to breathe properly. There's certainly not enough oxygen. Other than that, it'd probably be fairly cold as well most of the time. However, it's summer, and in the regions near the equator, or in what we would call the tropics, 25 degrees north and 25 degrees south, the temperatures can get as high as 30 to 35 degrees. These temperatures were recorded by some of the landers that are on the planet. However, even though it's nice and warm, 30 degrees, the overnight low was about minus 70 degrees centigrade, colder than Antarctica, enough to probably almost solidify carbon dioxide, certainly to solidify water. Regarding water, yes, there's plenty of water on Mars, but nothing liquid. Most of that water is trapped under the ground or in ice at the poles or at the extremities. And if any of it was to melt, even when we have a temperature of, say, 30 degrees, then it would evaporate straight away. We've got such a thin atmosphere, it would immediately boil even at those temperatures. and would disappear completely into the atmosphere. So no water to speak of liquid-wise on Mars. The planet is a planet of two halves. The northern half is quite flat. It's mainly plains, whereas the southern half is quite mountainous and rugged. They believe this is because about 4 billion years ago, something very large crashed into the very, very young developing planet, and hence this whole area here is virtually like an impact crater, but quite flat. Very quickly, let's see if we can see the other features at this time of the evening. It might be a bit dark. There's one that's a bit dark at the moment, but that's Valles Marineris, which I'll show you perhaps a better picture of later. And in the area just near that, there are 3 large volcanoes there, and it might be a bit dark on your screen, but in this area is the largest volcano in the solar system, called Olympus Mons, or Mount Olympus. It's about 400 kilometers across, 400 to 700 kilometers. It's 70 kilometers high, huge. There are some new craters in the surface, which I'll show you shortly. Let's see what else. Oh yes, the atmosphere is very thin. Why is that? Because Mars hasn't got much of a magnetic field. We're so used to that on the Earth. We use it for navigating and everything. And it also protects the Earth because the solar winds are deflected around our planet by its magnetic field. Mars has a very weak magnetic field. So the solar winds have been blowing past the planet for the millions of years and stripped away most of its atmosphere. So it's very, very thin atmosphere. Okay. I'll just show you, if you don't, just bear with me a moment while we take this out of full screen, and I'm going to go back.
Andrew, while you're preparing that, let's go on to Liam's talk.
Sorry?
While you're preparing your next section, we'll go on with Liam's talk.
Oh, I was just about to introduce Liam's talk.
Then go for it. I'll leave it.
Liam's got a copy of the running sheet, and so he knows when he's coming in. It's any second now. Okay, bear with us. Time's going pretty well. Okay, now I'm just going to share screen, but this time I'm showing you something that leads into Liam's talk. Go back to here, and I'm going to open. Okay, bear with me. Won't take long. Here we are. I should have had these open. I apologise. Let's get the ones we want. There's Olympus Mons. There's that one, and 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 that one. There we go. And we'll open those. Open. Sorry about the lag. I hope you're seeing all of this. There we go. Here's an example of some water on Mars. It's a crater, as you can see, but that is ice, water ice, and it's up to 1 kilometre deep and lots of kilometres across. So if we want ice on Mars, it's there. We've just got to melt it. So people going to Mars will be able to do that. Years ago, people thought there were canals on Mars, and this is a picture that we had from Sir Percival Lowell, who drew these by observing Mars through his telescope. And you can see these lines that appear to be there, linking what appear to be like centres of civilization, perhaps. But later it was found that's not the case. Here's a proper picture I hope I've got. No, I haven't got. A more recent picture would have found that's not the case. But here's a better picture of what we were looking at before, which is in the dark. This is Olympus Mons. That's a volcanic mountain. Here it is from above. Okay. And the last one I'll show you just before we go to Liam is this. This is what it would look like if we're on the surface of Mars. Very rocky, craggy, very dry, almost desert-like. But look at the colour of the sky. the sky is pink because Mars has lots of iron oxide, and a lot of dust in the atmosphere, which makes the sky appear to be pink. Now, how on earth could we get a photograph like that from the surface of Mars? And this is the cue for Liam to come on board. I'm going to leave my screen and hand it over to Liam, who I hope is going to show you how we got those pictures.
Thanks, Andrew. I have prepared a short presentation about the Mars rover mission for you. The first NASA rover sent to Mars was the Sojourner rover. It was launched in December 1996 and landed on Mars in July 1997. Running on solar power, its mission was to explore an outflow channel called Aries Valleys. The mission lasted 83 days. It had only been expected to last 7 days. NASA lost communications with the rover in September 1997, ending the mission. Since Sojourner, NASA has sent 3 other rovers to Mars. They were called Spirit, Opportunity, and Curiosity. Spirit was launched in June 2003 and landed in January 2004. Near the end of Spirit's mission, the right front wheel stopped turning. NASA suspected the power supply between the wheel and the motor was damaged beyond self-repair. Spirit dragged the broken wheel, creating a trench, resulting in the discovery of salts and minerals, suggesting that water had been in the area. In May 2011, NASA lost contact with Spirit. They believed that extreme cold had caused communication equipment to fail and declared the mission over. Opportunity launched soon after Spirit in July 2003 and landed in late January 2004. Opportunity and Spirit were both solar-powered, which became a problem during dust storms. Their expected life was only 90 days. Spirit went on to last 6 years and Opportunity 14 years. Their mission was to search for evidence of past life. Opportunity landed in the Eagle crater. It contained bedrock, so they moved on to the Endurance and Victoria craters to study. During this time, Opportunity traveled 45 kilometers. Communication with Opportunity was lost after a major dust storm covered Mars in June 2018. I recall Jackie speaking about the dust storms during Young Observer nights, and there was less features to see on Mars when I looked through the telescope. After many failed attempts to make contact with Opportunity, NASA declared the mission over in June 2018. NASA's rover Curiosity launched in November 2011 and landed in Gale Crater in August 2012. Its mission was to find out if Mars had the right environmental factors to support life. Previous missions used solar power to charge their batteries, which caused problems, particularly in dust storms. For the Curiosity mission, NASA used a nuclear power source, hoping to overcome these problems. Curiosity's mission was expected to last 2 years, but it's coming up to its 9th year on Mars. During its mission, Curiosity has been recording the weather, collecting rocks and samples to analyze, and exploring Gale Crater. On a family holiday, we visited the Parkes Radio Telescope in time to see Curiosity land on Mars. We saw the live video feed between Parkes, Canberra, NASA, and Curiosity on Mars. They turned Curiosity's cameras on about 20 minutes after landing, but all we could see was brown dust covering the lenses that was stirred up during the landing. We didn't see Mars. There are 2 new rovers being sent to Mars, one from the Chinese Space Agency and one from NASA. The Chinese rover is called Tianwen-1 and was launched on July 23rd 2020 and is expected to arrive at Mars in early 2021. It has an expected lifespan of 92 days. Tin Wind 1 is solar-powered and looks a bit like Spirit and Opportunity. NASA's latest rover called Perseverance launched on the 30th of July this year and should land on Mars on February 18 next year. Like Curiosity, it has a nuclear power source and it has an expected lifespan of 2 years. Perseverance will land in Jezero crater. Its mission is to explore the crater and take samples of rocks and soil to send back to Earth. Perseverance has a helicopter-like drone which attaches to the main body. This drone will be used to assist with exploration of Mars where Perseverance cannot reach. The drone is called Ingenuity. It is in the foreground of this image. Images and videos from NASA and Spaceflight Now. I'd like to thank Jackie for the great Young Observer sessions, Neil and Dad and the outreach team for help and support with the presentation. And thank you for listening. Thank you. Back over to Andrew.
Fantastic, Liam. Very well done. Everyone enjoyed that, I'm sure. And boy, are we looking forward to next year when they all start exploring. I'll very quickly wind up. I just want to do a couple more things. We will be as quick as we can. I'm just going to share my screen again. And there we go. So there we go. Just quickly looking at Mars, there's its 2 moons. You may see them if you've got good conditions over the next couple of weeks. Phobos close in, Deimos further out. But remember, Phobos is only 11 kilometres long, Deimos only 6.2, so you will need very, very good conditions. I'd like to wind up quickly with the account of whether there might be life on Mars. For years and years, we've had dreams about Martians. We've had books written about Martian invasions and so on. We even had lots of rumours about Martian life. As far as we know, there is none. The canals, which were seen by telescopes in the 1800s, were discounted when we had telescopes like Hubble, getting off the Earth and getting a better look, and there's no canals. People saw changes in colour as the seasons changed on Mars, and we thought, plants change colour with the seasons. No, there's no way that plants could grow on Mars.
Andrew, sorry to interrupt you just briefly, but you might want to put your redshift full screen so people can see it as big as possible.
Okay, there you go. How's that?
Beautiful, thank you.
Organic gases like methane, phosphine, which have been found on Venus, and a few other gases like that have been found. Again, under some circumstances on Earth, these gases will be produced by living things like anaerobic bacteria. On Mars, no. They've been produced by geological processes. There were even thought to be messages that came from Mars. When radio first came in, they thought they were picking up radio signals from Mars that seemed to have structure to them, but no one could work out whether it was real or not, and since then it's been discounted. Doesn't happen. Somebody even thought they saw a flash of light from the Martian surface pointed towards the Earth, and they even pointed the light back at Mars using mirrors. No response, no one there. So, sorry folks, at the moment, no way there's any life on Mars. The only hope we have is that maybe, just maybe, the salty lakes that are underneath the icy surface at the poles may contain some form of life, but it's a fairly slim chance, okay? You never know. Apparently Venus is our latest hope, so keep your hopes up. I'll now get out of sharing my screen and take you back, and thank you very much for listening. We'll look forward to your questions later. Thank you.
Well, thank you very much for that, Liam and Andrew. That was amazing. I know I'm glad to be back on Earth, but the trip was worth it. All right. Going to hand over to Neil again. He's got another one of our mini videos on planispheres this time.
Yes, this is almost a follow-up to the red lights video, and you'll see why when you watch it. A planisphere is an indispensable tool for astronomers. It's an all-sky map that you can use any day of the year. Let me explain how it works. On this planisphere, we have two sides, one for the north sky and one for the south sky. You'll notice that on the side, we've got these little tabs that we can turn the ring around with. That ring represents the progression of the night sky throughout the night and also throughout the year. You'll notice around the outside edge, we've got dates and times. Around the bottom edge of the circle, we've got the time in hours. Midnight is at the bottom. On the white ring, we have the date. What we need to do is line up the current date with the current time. So today's the 9th of September, and we're watching this at around 8 p.m. So let's turn the dial and see what is in the sky at this time. Now we have it set for this moment. If we keep turning, we will see the sky as it progresses through the night. So we follow today's date around the hours. If you keep turning, when you get to midnight, you will see what the sky is like at midnight. So in the west, the Milky Way is setting. In the south, we've got the Southern Cross right on the horizon. And out to the east, the sky is fairly empty at the moment. But if we keep turning, that is, we keep waiting for the hours to pass through the night, we will see the Milky Way rising in the east, along with Orion. So let's say we really wanted to see Orion tonight. Well, we turn the dial until Orion is visible and we have it nice and high in the sky. Then we look at today's date and see where it is on the time. So October 9th is at around 1 a.m. That's when Orion will be where we see it on the chart. To find objects on the chart in the sky, look around the edge of the white area of the sky. You will see down the bottom we have cardinal directions. This is south, east, and west. So when you're looking at the sky, you hold it up like this. So now we're facing south. If we turn around to the east, we turn the planisphere around. So the east is low, is towards the ground, and above that is the eastern sky. The converse is true for the west. So now we're looking west, and we turn the planisphere so the western horizon is at the bottom. If you want to look at the north, we turn the planisphere at the other side, and now we're seeing the northern horizon here. So we look with the north below us when we're pointing north. And that way on our planisphere, west is to our left and east is to our right. Why do we use a planisphere though, instead of using, say, a mobile phone app? Well, for a number of reasons. Your phone might not be with you, the battery might be flat, but the most important reason is that the screen will ruin our night vision. So if we don't have any light for the planisphere, how can we see it without ruining our night vision? That's where we get our trusty red light torch. Shining the red light torch on the planisphere will illuminate it perfectly without ruining our night vision. So a planisphere is a very handy tool to keep with you. Maybe keep it in the glove compartment of your car. That way it'll always be with you when you're out stargazing. It's a very handy tool to have, and you can plan your night's viewing with it. If you want to get your own, we're selling them in the Mount Burnett Observatory shop at mbo.org.au/shop. So go and pick one up now and you'll never be lost in the stars again. So the planispheres are actually just about to come onto the MBO shop. I just need to get some product photos to the website administrator so that we can get the listing online. But it will all be available for you very soon. So if you're interested in getting yourself one of these, come back and check our site, mbo.org.au/shop, in the next couple of days.
Awesome. Thank you very much for that, Neil. On to our last presenter of the night. We have Steve down in the bottom left-hand side there. Steve is a recent member of the MBO outreach team. He's been interested in astronomy since the early 1970s, and he spent a lot of time with people over the years discussing all sorts of topics associated with astronomy. Aside from that, he's a dedicated family man, and when he has the time, is also interested in psychology and 1950s science fiction books and movies. So, Steve, I'm going to hand over to you.
Oh, good evening, everybody. I'll just share my screen. Okay, hopefully you can see that. So the discussion tonight is a little bit about what we've all been experiencing over the last 10 months, I suppose. And the topic is what astronomy can teach us when it all seems a bit too much. So as Jamie said, my name is Steve. I'm actually a clinical psychologist by profession, but my other passion is astronomy. So I thought I'd try to link the two subjects together and see if I can lighten the load for you a little as we grapple with life in uncertain times. So the world today can be quite a scary and depressing sort of place. You know, we've all been hearing news about droughts and bushfires, and there's social isolation, financial problems that we might be experiencing. The list just goes on and on. And while no one can really make it all go away, sometimes it's helpful just to go outside and look up. It connects you with something much larger, and you may begin to appreciate that you're actually part of something truly amazing, something that really dwarfs the seeming immense problems that we encounter as we live our lives. And while all the issues that we confront each day may seem overwhelming, if you reverse your perspective a little bit, you may be able to put it into a totally different light. And nowhere can this be more fully appreciated than when you look at the image of the Earth caught in a sunbeam taken from 4 billion miles away by the Voyager 1 spacecraft back in February 1990. And you can see that little dot just there. The image itself is literally just a small dot, less than a pixel in size. It's located on an indistinct background, and when viewed without any context, many people could easily be underwhelmed and just promptly overlook it. However, on displaying this iconic image for the first time, Carl Sagan remarked, "Look again at that dot. That's here. That's home. That's us." That's the sum total of all our lives and experiences have occurred on that pale blue dot. Over 4 billion years of history, located on an insignificant but beautiful jewel lost in an immensity which we can never really fully appreciate or even conceptualize. And while this can serve to make you feel quite small and insignificant, the opposite is actually quite true. You are incredibly rare and precious. And after all, in all the vastness of the universe, there's actually only one you. So in looking at the night sky, something astonishing can begin to happen. Many people, on exploring the night sky for the first time, notice patterns. They start to connect the dots, both literally and figuratively. And for us in Australia, the most frequently recognised pattern is the Southern Cross, because it's the symbol of our country, and it can be seen all year around. And as you can see in this image, there's the Southern Cross there blazing away in the southern sky. Now, the sky is full of patterns which people throughout the ages have tried to interpret and get some meaning from. And with summer coming along over in the next few months, you might be familiar with the constellation of Orion, or the Pot, as many people like to call it. But if you look closely, and there's the pot there, you can see the base of the pot, and there's the handle. The star in the middle of the pot isn't a star at all. It's actually a nebula called the Great Orion Nebula, and there it is there. It can be easily seen with binoculars or a small telescope, and buried within the vast expanse of the Orion Nebula and many other deep sky objects that we can see in the night sky is a hidden delight. For within the heart of the Orion Nebula, right now, stars are being born. And over time, the stars that form within the nebula begin to process the planet formation using the material left over. The gaseous material becomes less visible, and the nebula then evolves into a star cluster containing thousands of newly born solar systems. The universe is a dynamic and ever-changing place. And in looking at the nebula, you can witness how it must have been before our sun started to burn hot in space. And looking at it, you can reflect on how amazing it is for all the right conditions to have occurred literally over billions of years for you to be here in the first place. You are the end product of a process which has been going on for around 14 billion years. Now, here's an example of a star cluster. It's called the Ptolemy cluster, and it's located in the constellation of Scorpius. It's a naked eye object, currently high in the western sky, and can be easily seen at the base of the Scorpion's tail. There are many star clusters like this, containing young stars, which are formed out of stellar nurseries like the Orion Nebula. And you can see the star cluster there, but look at all the billions of stars in the background. That's all part of our Milky Way galaxy. Over time, the stars and planets surrounding them start to drift away and move around our own galaxy. Our sun is just one in a galaxy containing hundreds of billions of stars. And our galaxy is just one of uncounted billions of galaxies situated throughout the universe. And in all of that, there's only one you. So now I'd like to show another image. This is an image of the famous Crab Nebula, or Messier 1. It was first seen by the Chinese in 1054, and this is the remnant of a supermassive star much larger than our sun, which had come to the end of its life and went supernova. The nebula lies about 6,500 light years from Earth. It has a diameter of about 11 light years and is expanding at a rate of about 1,500 kilometers per second. Now, remembering a light year is the distance that light travels in 1 year. And light travels at about 240,000 miles a second. So you can do the math. It's a long way. You need a good telescope to see it today, but the Chinese reported that they could see it during the day for almost a month after it exploded. All the heavier elements that make up our entire solar system, including ourselves, have all come from the ashes of long dead stars which have exploded in this way. And Betelgeuse, which is in the constellation of Orion, is a star that is thought will go supernova within the next million years or so. It might have already gone up, who knows? And there are many stars that explode in this way each year throughout the universe. Now, these images are just brief examples of how amazing the night sky can be once you really start to look at it. By looking at the night sky, you can directly witness the cycle of birth and life and death of stars. And we're no different, because everything that makes us who we are is the product of the same process. In this sense, there's no real distinction between us and the rest of the universe. We are all one and the same thing. So when you go outside and look at the night sky, have a think about it for a moment. You are an intimate part of a mind-boggling and amazing universe. You can see all that can be seen. Great clouds of gas and dust, stars that are being born, exploding stars seeding the galaxy with all the elements that hold the promise of life and intelligence, everything, including yourself. So, in conclusion, while we will always experience the ups and downs of life, it's possible to take refuge from all the stress and the anxiety and depression you may feel by simply appreciating your special place in the universe and the opportunity this gives us to get a sense of meaning and purpose. As Carl Sagan once so eloquently said, the cosmos is within us. We are made of star stuff, and we are a way for the universe to know itself. During hard times, be kind to yourself. Give yourself a break and look at the stars. It gives you an opportunity to get away from your problems by just being in the moment and being aware of all the wonder that's around you. Even if it is cloudy, you may want to consider that the true nature of the mind is like a still, clear sky, and that the problems we experience are like storm clouds, which can block the view. But always remember that the clear sky is always there. Looking at the stars allows you to connect with what is truly important, such as being with your family and friends, even if it's only by the internet, your values and your interests. It also allows you to appreciate all the little things in life, which when you really look are not that little at all. So I reckon there's a good line from an old Beatles song which summarizes it all, when they said, When you've seen beyond yourself, then you may find peace of mind is waiting there. And the time will come when you see we're all one and life flows on within you and without you. So just in case any of this has sort of raised any issues for you, I just want you to take note of these numbers. Obviously, in emergency situations, ring up 000, but you can talk to your GP. There's Lifeline, Beyond Blue, Parent Line, the Kids Helpline, and above all, stay safe and look up. So thanks for listening and good luck with everything. I'll just stop sharing. And here we are, we're back.
Awesome. Thank you very much for that, Steve. Such an important message there as well. Just got one more clip for you guys, and then we're going to move on to the question and answers. Remember, you can leave any questions you have in the comments. We're going to get to those in just a moment.
Hi folks, I hope you're enjoying this evening's stream. Coming up next, we've got your questions and answers, but before that, here are a few important messages. This series is made possible by a grant from Cardinia Shire Council. Thank you to the Council for that. Don't forget, this is a monthly series, so if you'd like to be notified when the next stream is going live, then follow us on our Facebook, Mount Burnett Observatory Incorporated, and you'll get notifications when we create new events. I'd also like to thank all the people involved in creating this series, including our President, James, the event coordinators, Kim and Jamie, our speakers, Andrew, Drew, and myself, Neil. Technical support from Paul and Anthony, and other support from Heike and Stuart. Now, let's hear your questions and get some answers. I just want to add to those credits. Sorry, Jamie. Didn't have the opportunity to add to those before we went live tonight, but I also need to thank Liam, of course, Steve and Jackie for her support as well. And there's been a crew working behind the scenes furiously to help out, including Peter, Saskia, Heike, and others. So thank you very much to everyone, the whole team involved in bringing this all together.
All right, thank you for those additions, Neil. We've got some new faces with us for the Q&A as well. We have Stuart and Jackie. So Stuart is a big fan of physics, mathematics, and especially space. He's been an MBO member for the last 4 years, and he enjoys helping MBO's outreach team and sharing his interest in science. He's presented a number of talks about physics during MBO members' nights, and he's actually undertaking a PhD in cosmology at Swinburne University, which is pretty cool. Jackie, on the other hand, has been an amateur astronomer for 30 years and has been active in outreach activities for 25 of those years. She spent 6 years under the dome at SciTech Planetarium in Perth and 17 years as a volunteer night tour guide at Perth Observatory. After moving to Melbourne back in 2014, she became a regular with the outreach team for Mount Burnett Observatory and is now the Director of Astronomy at MBO. All right, so going to move on to some questions now. I imagine we have quite a few in the comments here.
We won't be able to get to all of them tonight, but we'll do our best to answer a few good ones.
All right, so going to start off with a question from Emma. What type of telescope would you recommend for a beginner? Who'd like to answer that?
I suppose I've got to unmute myself for that one, hadn't I? Yeah, I know. I promised a few people a video on this, but it's not easy to give a simple answer. That's the problem, because it really depends what you want to do. The too long didn't read version is don't buy something that's based on magnification. So if it says up to 575 times, you should be running away from that. And basically you get what you pay for. If you come up to the observatory, we have what are called Dobsonian telescopes. They're basically Newtonian telescopes, so they have two mirrors in them. Andrew, you're blocking it. Yes, right behind Andrew. They look just like that, and you might think, "Wow, that's huge," but it's kind of basically what you need. Something like that. The other thing you might need to consider is also your expectations. Some people's expectations are a little bit too high on what they expect the telescope can do. Other people go into it with absolutely no expectations and they're just absolutely thrilled with what telescopes can do. If you want to do astrophotography, that's a whole other different kettle of fish. And then it depends. If you want something really big, you really need to mount it at home. If you want to go really mobile, you might need something smaller and accept that you're not going to get the really big view. So it's really, really difficult to say, just buy that one, because it really depends on your situation. And that's why I was hoping to do a slightly longer presentation, which would be outside of these kind of shows on it. So it's really difficult to really say, but basically, yeah, don't go for the cheap things. You get what you pay for in the telescope world. I think I'll leave it there. Thanks.
Awesome. Thanks for that, Jackie. Got another question here. I'm going to pop this one up on the screen, actually. This one is, what can we learn from black holes? Stuart, I believe as a physics student, this is right up your alley. Take it away.
Yeah, wow, that's a big question. Well, black holes are fascinating objects. I'm not sure I can give a definite answer to that question. Well, one thing that we can learn from black holes is that they are the densest objects that we can imagine. And they're kind of at the breaking point of our understanding of gravity. At the center of a black hole is what's known as a singularity. And in mathematical terms, a singularity is a point where your model just doesn't work. And so as a zero-dimensional point of mass being pressed down, it's kind of where our theory of gravity is accepted to stop working, and we have to try and unite it with quantum mechanics and all that other complicated stuff. So it's at the forefront of science to try and understand black holes. And now with our advancing technology, we're finally getting an eye open to how they work with the gravitational waves we've detected from them, and also from the pictures we've gotten from some of the largest supermassive black holes. Just now in our lifetime, giving us the first look into how black holes actually work in the real world. It's a fascinating time to be interested in black holes.
Awesome. Thanks for that, Stuart. Got another question here. This one is from Alicia, who asks, why did we send rovers to Mars? I think this one's a good one for you, Liam.
Agreed. Go for it, Liam.
Mostly to get a further understanding of the landscape, and yeah.
If I could add to that, and Liam, hopefully you can back me up, we're hoping to send people to Mars. So we have to know a fair bit about the planet before we risk human lives by sending them there. They're going to have to stay there for quite a while as well before they can come back home. So we have to know as much about the planet as we can. And also, of course, in the field of science, we want to know the answers to our questions. And Mars, as I'm sure all of you would appreciate, is one of the planets that everybody wants to know about. We still need convincing that there is or isn't life there, and a lot of the space probes are looking for signs of life. So yeah, there's some things we can't possibly learn by looking through telescopes or by simply scanning a planet from orbit. We'd have to get on the surface and actually explore what's there, what it's made of.
I'd really love to see Liam answer this question that Fran asked.
I've seen this question a couple of times. My favorite rover is Curiosity.
Why is that your favourite, Liam? What's special about Curiosity?
Mainly because it was the first rover I knew about, because I saw it at Parkes when we visited the radio telescope.
Good.
Okay, next question from Danielle. Are nebulas actually coloured, or is the colour added with a computer to show different gases? Neil, as our resident astrophotographer, this one's yours.
I can take that one. The answer to the question is yes, in both cases. So it's a little bit complicated, but I'll summarize it. There are two main ways that a nebula can have color, and that is via reflecting the light nearby or emitting light. So I'm going to put up a picture that I've taken a couple of years back, which will make it a bit easier for me to explain. So here we have an image of a region of the sky in the constellation of Scorpius near the big red star called Antares. So you can see this is Antares. Oh, my cursor is offset on my screen compared to yours. Okay, so this is Antares here, that yellow star. And the gas and dust around it, the nebula, is reflecting the color of that star. So it's an orange-yellow colored nebula. Nebula is the Latin word for cloud, and it's just basically a diffuse cloud of gas, dust, and other sort of space particles that are floating around between the stars. This star over here, there's actually a tiny little cluster of stars there. That's a star that's blue, and so it's reflecting the blue color of that nebula. However, if you look at this one up here, you can see the pink. Now, that is not a pink star that's illuminating it. So what's going on there? Well, most of the gas in these nebulae is hydrogen. Pardon me. And hydrogen gas, when it is nearby a very energetic star, it gets bombarded by radiation from that star. Mostly, most of the energy comes in the form of ultraviolet light. So you might know that if you turn on a fluorescent light, you're pumping electricity through it, and then it glows. Well, this is a similar thing. The electricity bombards the gas in the fluorescent tube, and the atoms absorb that energy, or some of that energy. But they're not stable. They can't hold on to the energy, so they have to spit it back out again. Well, because of the way that the universe works and quantum mechanics, atoms can only spit out energy in packets of a specific size or wavelength of energy, of light. And that wavelength happens to be in the pink part of our spectrum, in the reddish color. And so when you see a red or pink nebula, that is because it is glowing from the energy that is being absorbed from the star. On the other hand, though, the other part of your question you asked was, is the color added with a computer to show different gases? And sometimes, yes, that is the case. In fact, you can see in the background here, it might be a bit hard to see behind us, but there's a photo here. Pardon me again, got a bit of a frog in the throat tonight. That photo I took with special filters that pick out those wavelengths of light, so the red of the hydrogen glowing. But I used other filters to pick out sulfur and oxygen glowing as well. Now, to make an image, we need red, green, and blue. Sulfur glows in blue. Hydrogen glows in blue. Sorry, I'll correct myself. Sulfur glows in red. Hydrogen glows in red. And oxygen glows in sort of a bluish teal color. Well, that's not red, green, and blue. We can't really make an image out of teal, red, and red. So what astronomers do is that they assign those wavelengths of light to red, green, and blue. So we get a false color image, but the colors represent the distribution of the different types of gases in that nebulae. So if you're doing a narrowband false color image, yes, the colors are added by computer to show the distribution of the gases and the elements. But if it's just a color image, the colors that you get are actually the result of the colors of the gases either reflecting or emitting light.
All right. Awesome. Thanks for that, Neil. Got quite a few questions coming in now. Thank you very much, guys. Just going to find another good one. We'll go with this one from John. Given your specific equipment at MBO, what is the furthest but clearest object you're able to be confident you're seeing properly? Who'd like to answer that one?
I will. I think it's just about any telescope can see this. It's a quasar in Virgo, which is over 1 billion light years away. And it's just so bright. Even the 8-inch telescope, the 8-inch telescope behind Andrew would pick it up, because I've done it with my similar sized instrument that I own myself. It's about so a quasar is a black hole that's just really active in the middle of a galaxy. And this one is just super bright, and it's and I've forgotten the exact distance. It's either 1 or 2 billion light years away. So telescopes, people think telescopes see distance, and it's a really common misconception. Telescopes see brightness. Their nicknames are light buckets. They're buckets to collect light. And astronomers build bigger telescopes to collect more light. They're trying to see the faintest things they can, because the light as it comes towards us is gradually being dispersed. It's spreading out, so they need to collect as many photons as possible. That's what they're trying to do. They're not trying to see in the distance. And the thing to think about is trying to see the closest star to us past the sun, Proxima Centauri. Just about everybody's heard of Proxima Centauri. It's a little red dwarf. It's really hard to see. It's hard to see. But you can go and stand outside and see the Andromeda Galaxy over 2.2 million light years away. You can see it with your naked eye. So things can be really close and we can't see them because they're not showing us any light, but things can be a long way away and be really bright and we can see them easily. So it's all about light. Thanks.
Thanks for that, Jackie. Got another question here. This one's from Gage, who would like to know if we can time travel by going into space. If I'm reading that correctly, I believe that relates to the theory of relativity. So I'm going to hand over to Stuart for that one.
Yeah, no, I'm a big fan of time travel. It's great fun. One thing needs to be said. If everyone just waits for 1 second, congratulations, you've all time traveled 1 second into the future. If from one perspective, we're all just time traveling. And what relativity deals with is the rate that you time travel. So we haven't discovered any way to travel into the past, but relativity describes how we time travel into the future. And that's where things get pretty interesting, especially going into space gives you more opportunities than on the ground. One famous example is the twin paradox, a interesting thought experiment for special relativity, where someone who travels extremely fast will travel slower in time. So if you have two twins, start on Earth, one gets in a spaceship and flies far away to a distant star, and then comes back, the person on Earth will observe them as moving incredibly fast, and so we'll see them traveling through time slower. So they will be younger than the one that stayed back on Earth. And another fun thing that general relativity brings into it is that it slows you down through time as well. So if you're really near to a black hole, you'll also travel slower through time. And if you're in the depths of empty space, you'll actually travel faster through time. So the very core of relativity says that space and time are linked. So how you travel through space affects how quickly you also travel through time, through the a bit fairly complicated equations that Einstein came up with that I probably won't have time to go through here. But yeah, no, time travel is incredibly interesting, and the intricacies or that general relativity allows you to get away with is an ongoing area of research as well.
Actually, a couple of the astronauts who spent a long time in orbit are a few seconds younger than they would have been if they hadn't gone into space. No one's noticed the difference, though, for some reason.
There we go. Time travel is real. Next question. This one's from Kylie. Why is Pluto defined as a dwarf planet? And it appears as though we have no audio from Drew, unfortunately. Apologies, folks.
It's probably
I'm sure Drew has a very informative answer for us. Unfortunately, we are still battling technical difficulties. So we'll put that question on hold for now, and we'll pick on another one. This one is another physics question. Sorry, Stuart. Can you travel faster than the speed of light? And if not, why not?
Oh yeah, no, I love answering physics questions. Could do it all day. Yes, that one of the interesting outcomes of relativity is that you can't travel faster than the speed of light. It's the cosmic speed limit, as they like saying. And things get a bit complicated and wibbly wobbly, space and timing. But one practical way of understanding why you can't travel faster than the speed of light is that the faster you travel, one way of visualizing it, though it maybe isn't as common in scientific circles, an easy way to visualize it is to say that your mass also increases. The result of which is that it's harder to push you faster once you're already traveling fast. So something that's traveling very close to the speed of light, you have to put a lot of energy into making that go faster. And the math works out such that it takes an infinite amount of energy to push something up to the speed of light. And at the speed of light, it would also have an infinite amount of mass that would immediately suck everything up in the universe and whatnot, kill us all, whatever. Infinities are fun to deal with when you plug them into physics equations. But yeah, a lot of things break down when you start traveling at the speed of light and you have mass. Light can only travel at the speed of light because it doesn't have any mass. It can't travel any slower or faster. So yeah.
All right. Thanks for that, Stuart. Got another question here. Do large objects with strong gravity or magnetic fields affect time? This one's from Charlotte. Who'd like to answer that one? Stuart again.
Yeah, no, no, big fan of time travel. Always answer those questions. Yeah, so I mentioned before the strong gravity. Yes, that definitely affects time. Gravity, in a way, is how space and time are interacting at that point. If you want to get really metaphysical, the gravity is a effect of the curvature of space and time. But that's getting a bit too technical. But yes, in strong gravity, time will travel slower. So if I fly around a black hole, I'll age slower and experience less time, come back younger, and then someone who stays away from the black hole. I believe that's the way it works out. Hopefully I got that the right way around. Magnetic fields, not so much. Magnetic fields are not intrinsically linked with the concepts of space and time. They're kind of another field that exists in space that travels amongst it. But it is worth mentioning that a magnetic field contains energy. And thanks to Einstein's famous equation, E equals mc squared, energy is equivalent to mass and vice versa. And so at a very basic fundamental level, it's energy that creates gravity. So although it will be incredibly small, a magnetic field does have energy which will ever so slightly warp the fabric of space and time, though we likely won't find a situation where we will be able to closely measure that. Though one final word, it does, thinking about these two concepts reminds me of neutron stars. I won't go too into detail, but neutron stars are incredibly dense and very interesting objects. They're basically the densest object you can find in the universe without getting to a black hole. And neutron stars have ridiculously strong magnetic fields. If you're gravity will literally squish you at the surface, yet the magnetic fields are still strong enough to lift atoms off the surface against gravity. Neutron stars are insane places, but I suppose if we have to find anywhere that magnetic fields, if you have to take into account general relativity when dealing with magnetic fields, it's around neutron stars. Still a very interesting area of scientific research, just figuring out what's actually happening on the surface of a neutron star. But yeah, I better stop talking.
It's great, Stu. Thank you for sharing your knowledge. Following on from what you said about black holes, though, we have a question from 10-year-old Emmy. What would happen if you fell into a black hole? Now, for this one, it would really depend on what size the black hole was that you were falling into, because there is something called a spaghettification force that happens when something is falling towards or into a black hole. So the smaller the black hole is, the stronger the spaghettification force is. So basically what a spaghettification force is something essentially turns into a piece of spaghetti, if you like. It stretches out, it gets really, really long and really, really thin. And it actually starts to go a little bit red as well. So it appears redder to an outside viewer. So we have a supermassive black hole at the center of our galaxy. Nothing to worry about. It is several tens of thousands of light years away, so it's it's nothing to be concerned about at all. But that one would have a lower spaghettification force than what a smaller black hole would have. So black holes, for those who don't know, are dead stars, and all of their mass has been compressed into a very, very small space, and their gravity is immense. And Stuart was saying before that stronger gravity affects time. This would happen as well if you were falling into a black hole. If you were wearing your watch as you were approaching the black hole, time would slow down. It would feel the same to you, but from an outside perspective, someone looking at your watch would see the time go slower and slower and slower until eventually you stop, and you don't actually see something go over the event horizon of a black hole or fall into the black hole. It seems to stop just on the outside. So that's essentially what would happen if you fell into a black hole. So I don't know about anybody else. I'm not game to try it. If you want to, as a science experiment, that's up to you. All right. Stuart, if you wanted to add to that with your physics knowledge, feel free. But that's about all I've got.
Yeah, no, you covered the important, interesting points about black holes. There's a lot of crazy things happen when you fall into a black hole. I probably couldn't even remember them all just now, but yeah.
It was one of my favorite sections of the encyclopedias I read as a child. I actually had quite a few of those in my youth. My first one I read cover to cover at the age of 7, for those who didn't know, which is actually going to be everybody that's watching this stream. Unfortunately, we are starting to run out of time now, though. Just going to find one more question. Just bear with me. Sorry, folks, we have quite a few questions that have been coming in throughout the night as well, which is great to see. As I said, unfortunately, we won't have time to get through all of them tonight. But as we mentioned, this is a monthly stream, so we will be running these for the foreseeable future. So just give us 1 second. We're just going to do, we'll do a couple more questions. We have one here. Are there any exoplanets that are similar to Earth's orbit? So are there any takers for that one?
If yeah, someone else take it if you want.
Yeah, I may be able to answer it. I believe, are we talking about what we call the, is it the Goldilocks planet? Is that it? It's not too cold, not too hot, it's just right. Is that what we mean? If so, they keep finding them every month. I think there's probably hundreds by now of exoplanets that would have similar conditions to Earth. We can't be sure about what elements are on the planet, but the temperature conditions would be right. The gravity would be okay. We could survive there. So there's probably by now hundreds. The first few were found quite some time ago. But they're always on the lookout. So there's probably a new one discovered every month or maybe even every week. So there's plenty. There's plenty. To get to them, though, that's the big problem because they're all light years away, many hundreds, sometimes millions of light years away. So getting there is going to be a problem. We need someone out there to discover a way of traveling faster than light, which apparently is impossible, but lots of things used to be impossible, and they're quite possible now.
All right. Thanks for that, Andrew. We're going to move on to our final question of the night. If we didn't get a chance to answer your question, we apologize. We had quite a few coming in, as I said. We're going to end with our question of the night. Now, this one, we have a bit of a surprise for you guys. The question of the night is actually going to be receiving their very own planisphere, as you can see Neil holding up there. So this one was from Liam, age 7. Would like to ask our Liam if you can see the rovers on Mars with a really strong telescope.
Unfortunately, no, but there has been a orbiter that has taken an image of one of the rovers.
Awesome. Thanks for that, Liam. All right. So Melissa, who has Liam age 7, if you can send us a message and we'll organise getting you the planisphere. That'll do us for tonight. Unfortunately, we didn't get a chance to go through all of the questions. But if you guys want to come along to the next episode of our Night at the Observatory series, bring your questions along, post them in the comments again, and we'll do our best to answer all of the questions as best we can. As Steve said at the end of his presentation, stay safe and look up.
Mm-hmm.